So let's jump in and talk about how we use regression modeling to make predictions. After all, we refer to regression modeling as predictive modeling. So recall that our general linear formula is given by the equation y equals beta x plus alpha, where y refers to our dependent variable, or outcome of interest, x refers to our independent variable, beta refers to our slope coefficient, that is rise over run, or how much we expect y to change given a 1-unit change in x, and alpha equals our y-intercept. So it's important to take a step back at this point and think a little bit about what regression analysis is doing and what it's not capable of doing. So what we're really trying to do with regression analysis is to identify whether or not there's a relationship between two variables x and y. Now, in reality, there is or there is not a relationship between those values. As we said before, either in reality the null hypothesis is true or the null hypothesis is false. So in reality, there is a true relationship between x and y. What we're trying to do with our analyses is to estimate that relationship. So in this regard, the true values of beta and alpha are not known. In fact, we don't even know if the relationship is linear. That's an assumption we're making with our modeling choice. So what we're really trying to do then is we're trying to estimate the values of beta and alpha to the best of our ability with the data that we've obtained. So when we're dealing with prediction, we're going to start being a little bit more precise with the way that we're using these terms and using these concepts and kind of how we calculate them and then frame them in terms of prediction versus reality. So here we're going to say that the regression estimates of our values are beta hat. You can see we have a little accent on top of the beta. Beta hat will refer to the estimated slope we get from a regression analysis. And alpha hat, once again note the little accent above the alpha, is going to refer to our estimated y-intercept. So we can therefore predict the individual value of y, that is y hat I, where y hat refers to the predicted value of y from our model, I refers to any given individual, as a function of beta hat, or slope estimate, times xi, which refers to the given value of x for any individual I, plus alpha hat. In other words, we can take any value of x, that is xi, plug it into our equation, and then generate a predicted value of y, which we're calling y hat I. Now, I'm aware this sounds a little confusing, so let's go back to our example with midterm grades and final exam grades. So we ran the regression on midterm grades and final exam grades, and we found that the slope estimate was equal to 0.98, and the y-intercept estimate was equal to 1.05. We can therefore say that we can generate a prediction for any given individual by multiplying the midterm grade of the individual times 0.98 and then adding 1.05. So let's assume that person I gets an 80 on the midterm. What would be our predicted value for their final? Well, their predicted value for the final would be plugging 80 into our equation, then solving for y hat I. So here we would have y hat I, that is our predicted value for the final exam for person I, is equal to 0.98 times person I's midterm grade 80 plus 1.05. If we reduce that down, we would get a predicted value of y hat I is equal to 79.45. So someone who has an 80 on the midterm, plugging that in gives us a predicted value of 79.45. So we can plug in any values of x and solve for y, and that gives us a predicted value of y for a given value of x. If we do this for a range of values, that those data points actually define a line, which is our regression line, or what we might call the prediction line. That is, the regression line, as defined by the estimates, gives us all of our predicted values of y. So the real interesting question then about predictions is how accurate are our predictions? Our regression line is going to generate a prediction line or a regression line, which allows us to predict values of y for any given value of x. Now keep in mind that the more variation there is in our data, the less accurate our line is going to be, and therefore less accurate our predictions are going to be. We can calculate, however, predictions for any value in our data set and compare the actual values of y to the predicted values. Note that you can also create predictions for data that do not appear in your sample, but you won't have any actual values to compare them to. So using the data set that I used earlier in the video series, there was actually no student that received an 80 on the midterm, so there's no way to compare our 79.45 to an actual data point. However, there are lots of values that are in our data set that we can compare their predictions to those actual values. So here we can simply define prediction error, which we're going to note as epsilon I, that is the prediction error for any individual I, as being the difference between our observed value, that is simply yi, minus our predicted value y hat I. So intuitively, the prediction error is simply the difference between where you really are on y and what we predicted you to be on y. Now, once again, that sounds a little abstract, so let's follow up with an example using our midterm grade and final grade example. So once again, here's our scatter plot overlaid with our regression line, the regression line being y is equal to 1.05 plus 0.98 times x. So any value that falls on the line is our predicted value for y given a value of x. Now you can see here that a lot of the points don't fall directly on the line. So I've illustrated the difference between the point and the line vertically with red lines here, and that red line shows the error or the difference between each predicted value and the observed value for each observation I. In other words, each red line represents epsilon I, which is the difference for that individual value and its prediction. So let's reiterate a couple of these points. So first, we said that we can generate a prediction for any observation xi by multiplying the slope coefficient times the value of x and adding the intercept. This produces our predicted value of y for a given observation, which we denoted as y hat. We said that for every y hat value, we can look in our data set and we can calculate an error for each individual observation. So we said that the error, that is epsilon I, is the difference between the observed value of y, yi minus the predicted value of y hat I. So therefore, kind of using our rule of addition, we can say that the actual value of y is equal to beta hat xi plus alpha hat plus epsilon I, or in other words, the observed value of y is equal to our estimated value of y, which is determined by beta hat xi plus alpha hat, plus the error for that observation. Now, the real interesting part is really what causes the error in these models. And that is, why are we getting a misprediction? Well, part of the misprediction, or really what the misprediction is all about, are what we call omitted variables, variables that have an influence on the outcome, but we're not directly measuring. So here we can think about, well, what are some of the other factors that have an impact on the final exam that are not related to the midterm? And it might be the amount of hours that they studied increased. It might be that the material was more difficult on the final exam than was on the midterm. So really any of those other variables that could impact y that aren't being measured directly in the model will automatically dump into epsilon and cause error in our analyses. So regression modeling in practice is all about trying to control the error or add in more variables that account for the error in the model. We'll talk a little bit more about that in the future when we talk about multiple regression modeling, which is including more than one independent variable in the regression analysis. Let's take a closer look at how we handle predictions and errors with our midterm and final exam data. So this is the same data that we use to generate the regression line of a slope coefficient of 0.98 times midterm grades plus 105 to generate the final exam grade. So in column C, I'm going to generate the predicted values of y. I'll refer to that column as y hat, and y hat will be equal to our 0.098 times our midterm grade scores, in this case for observation C2, the value in A2, and we're going to add 1.05, which is our y-intercept, or our constant. If we hit enter, we get our prediction value of 84.35 for the first observation, and we can fill in the rest of the predicted values for all of the columns by dragging down sort of that bottom right corner. So now that we have all the predicted values, we can see that we have an 84.35 for observation 1, an 88.27 for observation 2, and a 91.21 for observation 3. What you can also see here is that our predicted values closely match the student scores on the midterm, but in a lot of the cases, the final exam scores are quite different from our predicted values. So we can generate the error, that is the difference between our final exam score and what we expected, in column D. So the error, once again, epsilon I, is going to be equal to our actual value of y, in this case B2 for observation D2, minus our predicted value in C2. If we drag down that right column, we get all of our errors. And you can see here that any overages in our prediction will show up as negative errors, and any underages will show up as positive errors. So for observation 1, the person received an 80. In reality, our model predicted an 84.35, so our prediction error was a negative 4.35. That is, that negative 4 represents an over-prediction of what the student really received. For person number 2, we can see that the person received a 90 on the final. Our model predicted an 88.27. So here we have a slight underage, as we are under-predicting that person's score by 1.73 points. Person number 3, finally, as our example, received an 86, and that person had a prediction value of 91.21. So we over-predicted person 3 in our observational data by 5.21%. Now, once again, it's important to keep in mind that once we have a regression equation, that is, once we have an estimated slope and y-intercept, we can generate predictions for any value of x that we want by simply plugging that value into our equation. Note, of course, that we can only generate errors when we have an observed value of y that corresponds with that value of x. So, for instance, we use the hypothetical value of 80 in our previous couple slides. And note here that no student received an 80 on the midterm in the actual class. So here, if we plug in an 80, we can get that predicted value of y hat as 79.45, but we can generate no error because no student actually had an 80, and then therefore had a final exam score to compare our predicted value of y hat against an actual value of y. So as some concluding points, regression modeling can be very powerful. You can use regression modeling to predict outcomes. Keeping in mind, though, that the error could be a problem for your prediction, and that the error has substantive meaning, which is really capturing all of the things that could affect the outcome variable that aren't included in your model.